no more surprises there. And the first one is going to be given by Professor Muller-Hartmann from the Institute of Theoretical Physics at Cologne. And he's going to talk on Wannier functions for hybridizing states of transition metal oxide, chains and ladders. Professor Muller-Hartmann.
Thank you, Chairman. Before starting my talk, I got to make a short remark. When I received the invitation to attend this marvelous meeting, I responded to Krish by an email saying that I would love to come, but they had a problem. I felt unable to provide an appropriate and sufficiently profound contribution to this meeting because after my retirement 5 years ago, I made a bold decision. You may call it an outraging decision maybe, but namely the decision was that I turned my curiosity away from solid-state physics towards pure mathematics. And there are certain topics which I always had wanted to learn closer, and so mainly in number theory. And well, I mean, incidentally, this is a completely different world, number theory and solid-state physics. If I just compare the speed by which new ideas and concepts are emerging and problems are being solved in solid-state theory, as it is exemplified by this meeting, to that speed in number theory, where problems which emerged several hundred years ago still await their solution. That reminds me something which I learned from Muller the other day. Well, if you go from solid-state physics to number theory, that is like going from Bangalore to Varanasi. Well, the response I got after my message to Krish was then that I was welcome in any case. And so I must say I don't know how to express my gratitude for this very generous response. Well, I mean, finally, I assembled enough courage to decide offering a talk, but a rather unpretentious talk, as you can imagine, and on a very special topic, which all of you are quite familiar with. And so I just wish to ask you to lean back and imagine you are in Varanasi, and my only hope is that I will not be too boring to most of you. So you have seen the title of my talk, and I'll go on to the outline. I think it's for the hybridizing oxygen orbitals in low-dimensional systems, and in order to have a basis for this discussion, I have to start by reminding you something which you know better than me, probably the modern of two-plate planes, because that forms the basis for what I will talk about then later. So I will briefly describe the three-band model with a strong focus on what I call the hybridizing 2p states, and their description by a Wannier function as it was introduced by Zhang and Rice. And I will then explain what the use of these Wannier functions is. Wannier functions, as you know, the more useful, the better they are localized. And that's why I had always thought in one dimension there's less localized, and I always thought they are not useful at all. So the method of Zhang and Rice was not useful in most one-dimensional systems. And I believe that until recently, when I, in a small collaboration with one of my experimental colleagues at Cologne, I helped them to understand the electron dipole moments on the copper side of copper oxide system, the one-dimensional systems where we're making optical spectroscopy on, that I realized that if one does a proper modeling of low-dimensional systems, one gets excellently, namely exponentially localized Wannier function for most of them. And that is the main topic of my talk. That's all. I mean, there's nothing else which is newsworthy in my talk. So I already disclosed part of the summary with this remark. Well, I will then exemplify that by at least two of these systems which are shown over there, and depending on how much time will be left. You all are aware of the fact that we are this year celebrating the 25th anniversary of the discovery of high-TC. Becknott and Muller published their work early in '86, I think in March or so, in Zeitschrift für Physik. Zeitschrift für Physik is a journal which had a great history, of course, but one should also be aware that outside Germany it was hardly read by anybody, and so that's the reason why only towards the end of '86 the international community became aware of the fact that there was something important. Actually, I heard that there was a saying that some colleagues said Becknott and Muller were hiding their work in an obscure German journal at the time. And so that is also the reason why the first paper of how one would have to model the electronic properties of this lanthanum and copper oxide 214 system appeared about 1 year later after the publication of the experimental journal by Phil Anderson. And yesterday already it was mentioned at one point that this publication has a very close relation to Bangalore. And well, I mean, this is just showing the orbitals which are important for the electronic properties of the system. So we have here this 3D orbital in which the hole is an undocked system, and then the hybridizing oxygen orbitals in between. But I showed yesterday already this paper on the international conference on valence fluctuations in Bangalore, and of course in this conference the ITC was not on the scheduled program, but it was discussed in the intersessions quite a lot, and then it was decided. Anderson one night wrote a couple of transparencies and gave a talk which had not been scheduled in the program of the conference, where he described to us how we should model this system, the oxygen, copper oxide planes in the system. And this talk was essentially the basis for his publication, as far as I understand, in Science. And you see here, of course, Phil Anderson standing, and as I showed already yesterday, Rama right besides him. Well, let's then get to the three-band model. We have here a unit cell which shows that there are 3 orbitals per unit cell in these copper oxide planes. You all know that very well. And so that's why it's called a three-band model. And the model Hamiltonian contains these 3 well-known terms. First one describes the orbital energies of the 2 orbitals, the covered unit term, and then the hybridization term, which describes the hopping of the electrons. The Lorentz scheme for the first 2 terms is such in the whole representation that in the undoped system the holes go into the copper side, but the Hubbard repulsion serves such that if you dope the system with holes, that the additional holes go onto the oxygen. And the typical model parameters for this model are given here. So first one is the distance between the p and the d orbital, the Robert U, and then the Hopper matrix elements. And it looks as if the Hopper matrix element is, or rather, it might be used as a small parameter. But it turns out that this parameter is too big for a straightforward perturbative treatment. And we have made a detailed study about 10 years ago of the description of the low energy part of the three-band model by the TJ model and its extensions. And what I'm showing here is, as an example, is the nearest neighbor exchange coupling, superexchange coupling between two copper sites, J1, in a direct perturbative expansion with respect to the Hopper matrix element. What is shown is the exchange coupling in units of the lowest order term, which is the fourth order term, because for having a superexchange, the hole has to hop from the copper side via an oxygen side to the next copper side and back. And so this ratio is, of course, 1 for small exchange coupling. What you see here is then the 6th order, 8th order, 10th order, 12th order polynomials, and you see that the radius of convergence must be somewhere here. And this is about half of the value, of the physical value. Of course, as physicists, we know that there are methods to extrapolate beyond the radius of convergence, such a, if it has this information at hand, namely via Pardee approximants, and if different Pardee approximants lead to similar results, then we are confident that this is a reliable extrapolation. I know that mathematicians don't like this method, but what is kind of uncontrolled. Well, anyway, but I mean, such a treatment is of course not very convincing, because it doesn't tell you anything about what is going on. I mean, you don't want to make high order expansions, but I mean, what is more important is that you don't understand what is going on. And at that point, then, well, I mean, this actually, but I think this uncertainty led to the fact that not everybody in the community was agreeing with the conclusions which Phil Anderson had taken them, that this would lead, the overall energy sector would be a TJ type of model. I think Dick Emery, I think, were among the people who had different opinions. But I mean, this uncertainty was then removed 1 year later by the work of Zhang and Rice. And, let's then look closer at the hopping Hamiltonian. Oh, so this is, oh yeah, well, okay. That looks a bit funny. There's something wrong with this formula. Yeah, is there? Well, it's not so important. It's not so important. But the details are not important. And so, if you have a closer look at the hopping Hamiltonian, we see that it describes the hopping of a hole from a copper site to a linear combination of the 4 neighboring sites, oxygen sites, right here. And so, this is a hopping to a state which has a norm of 2, and if you normalize it, we call the normalized hybridizing hopping state, oxygen state, little h, then the hopping Hamiltonian has this form. There's a factor of 2 TPD coming in front. So 2 TPD is a better estimate of the real coupling constant. That is not so small anymore, and that explains why the rate of convergence is exceeded by the physical value of the TPD. Well, one might now have the idea to introduce this state H as a basis state to describe the model, to make a transformation, but this does not work so easily because there's a problem of non-orthogonality. Neighboring states have an overlap of 1/4, and that problem was then solved by Zhang and Rice by introducing a Wannier state to describe this state little h. And So this is the reference. And what one has to do is technically to find this Wannier state. So really there's something wrong, but I can't describe it in words, I think. So the first step is, well, it's a pity. First step is one describes one goes to the momentum representation for the state in the momentum representation, which is not visible at all, well, where these momentum states, they are eigenstates of different values of the momentum operator, and so they are orthogonal to each other, obviously. But they're not normalized. And so one normalizes them, the normalization, the norm of, oh, it's terrible, is given here by a square root of sum of two squares of sines. Is there a chance that this can be used? Oh, no, probably not. Well, I mean, I can try to well, you know this anyway. I mean, I'm boring you, I believe. So, I mean, so we have here then the normalization factor in front, and then these states are normalized, orthonormalized states. These are the Wannier function states in the momentum representation, the Baryon zone. And then what you have to do is just go back to lattice space, and this transformation is a unitary transformation. And so you get then, of course, in the lattice representation, you get states which are orthogonal to each other on each pair of sides on the lattice. And this product if you go to lattice space, then of course goes over into a convolution between the Fourier coefficients of this normalization factor and the Wannier states. And yeah, I mean, I'm showing here the values of these Fourier coefficients, and also formula for asymptotic behavior for large distances, and this is a minus 1 over a 2 pi factor, which is not unimportant, times the third power of the distance. So, I mean, the decay is not very strong, it's not exponential. Of course, this algebraic decay is due to singularity of this function at k vector 0 in the center of the Baryon zone. And in a sense, Sun and Rice were lucky that this factor of 2 pi appeared here, because that's a small factor. So what happens is that the on-site matrix elements is very close to 1, and the others, mainly due to the 2 pi factor in the denominator, are really very small. They don't decay very fast, but they are small enough so that this opens a chance to, well, I mean, this is the formula for the Wannier state, which are not so important here. And this is a picture of the coefficients of the Wannier states. We can skip this. It's terrible. I don't know what. Well, what one can do now is the following. One has this strong local term, and one can split this from the hybridizing Hamiltonian APH and put it together with the first two terms of the Hubbard model, of the three-band model, and then one has a local Hamiltonian which contains a large part of the hybridization. And then the remaining terms have these small factors Tm, which is then a smaller perturbation. And so on, and this local Hamiltonian here, which contains which contains this local part here. This is of course side diagonal, and so it describes atoms, and you can solve this, diagonalize this exactly. And of course the ground state of the two-hole sector is the famous Sun-Rice Zinlet. And that was, of course, a conceptual progress which clarified what is going on in this system, namely, and the perturbation with respect to this term converges wonderfully, and so there was no doubt anymore that this type of description and the transformation and the description of the low energy factor by a TJ model was absolutely correct. And in our work 10 years ago, we have also looked closer at this perturbation expansion, and you see that low order expansions with respect to the remaining hybridization leads to a perfectly convergent behavior. And the thick curve here is the fourth order term. And this perturbation expansion is compared to the 2 per day from the direct expansion, and they coincide very well up to here. Okay, this is the introduction and a reminder at the history of the three-band model. Now, if you look at one-dimensional systems and you model them just by a naive couple oxide chain, for instance, like as it is given here, then this normalization factor is just the square root. No, it's just 2 times the sine of k. It's the same square root, but only with one term under the square root. And so the Fourier coefficients are like that. They drop fast, less fast, of course, in the 2 dimension only with the square of the distance, and the formula for the Wannier function is this, so the amplitudes are going down only with the first power of it. And it turns out this is really not very useful. That's what led me to think that the method is not, manifestations are really poorly localized and doesn't work. So the question is now whether this is a general shortcoming for one-dimensional or quasi one-dimensional systems, and the answer is, which I learned about 2 years ago, not at all. This poor localization of the hybridizing Wannier functions is only present for 180 degree superexchange. That is one aspect, and I will give an example for that. And it can be avoided by adding what I call spectator oxygen ions, which are always present in real systems, because the coordination, oxygen coordination of transition metal oxides is I think never 2, or it's always larger, 4 or even 6. And I will, as a first example, I have chosen the copper germanium oxide, which is probably also known to most of you. That was discovered in 1993 by Arthur as the first non-organic pious compound, spin pious compound, and it contains copper O2 chains which are produced by attaching these oxygen copper O6 octaedra along edges. And so that leads to a topography of the chains where the superexchange angle is rather closer to 90 degrees than is 99 degrees and not 120 degrees. So a superexchange process would take place that a hole goes from this orbital to an orbital here. I mean, the orbitals which are shown here are the crystal field eigenstates of the oxygen sites. And pardon me?
What is this 180?
180 would be straight. If the next couple would be up here, that would be 180. But here Here it's 99 degrees.
Zero?
Zero? Well, zero doesn't, that would mean that the two coppers are at the same site. I mean,
Zero is direction, so what is the angle between?
no, the angle between, well, it's just, it's this angle here. This is 99 degrees in this case. Yeah, and of course in a straight chain it's 180 degrees. And you look at superexchange path. That is the usual terminology for the superexchange angle, isn't it? Yeah. So you see here, you know, I think also all students probably know that if the superexchange angle was 90 degrees, then this hole would go into an orbital which is orthogonal to the orbital into which this hole would go. And so the leading term for the antiferromagnetic exchange interaction is not present anymore. And you also know that it leads to an effective ferromagnetic, a small ferromagnetic exchange, and that the process which produces that is a process where you have as an intermediate state two holes on the oxygen side. And then the Kunsel coupling on the oxygen side leads to a splitting of these two hole states into triplet and singlet, and so you get a difference between the ferromagnetic contribution, which is somewhat larger than the antiferromagnetic one from the singlet, and that leads to this effective rather small ferromagnetic exchange, super exchange in that case. So here, it turns out in copper germanium oxide, the super exchange is small but antiferromagnetic. And well, I mean, the fact that for 90 degrees we have a zero range for the Wannier states, because the Wannier states, I mean, the hole cannot hop at all further, and so the Wannier state is just the state which is formed by these four orbitals which with this direction. So that shows already that if the angle is 99 degrees, you would have an exponential localization of the Wannier states. Well, this is also this gives the crystal. There's a picture of the hybridizing orbitals. So here it goes into this orbital, and from here it goes into this orbital, and they are also orthogonal, or almost orthogonal to each other. Terrible formulas. Well, anyway. Well, if you do the calculation, you get the formula which confirms what I just said. You get as a normalization factor a function which has a square root of a 1 plus a sine, cosine, plus that is a sine of the angle delta, which is not visible. I'm sorry about that. And so this is a perfectly analytic function in real k as a function of k. And that means, of course, that the Fourier series converges exponentially well. And one can terrible formulas. And one can again calculate analytically with the formula for the asymptotic behavior, and is the tangent of this delta angle over 2 to power distance by which it decays. And so numerically you have here a large on-side term, and then a really exponentially very fast. So in this case we have these Wannier states are perfectly useful for doing quantitative calculations. The second example is a system where we have zigzag chains of copper oxide, and I better show this one. So this is a picture of this zigzag chains of copper oxide. But it turns out that these two parallel chains, if you look in the horizontal direction, they are magnetically very well decoupled. So this system strontium copper O2 is considered a very good realization of copper oxide one-dimensional copper oxide chains. And the fact that these chains are decoupled is obvious because here we have between these two neighboring on the zigzag chains couples, and we have a 90 degrees superexchange. And I just told you, explained to you, reminded you the fact that this would lead to a small ferromagnetic superexchange between these neighbors, whereas in chain we have a strong antiferromagnetic exchange. That means in mean field approximation that these chains are completely decoupled, and because this ferromagnetic superexchange here is frustrated by the antiferromagnetic, strong antiferromagnetic superexchange. And so what we have here is now this is a one-chain system, and I'm showing this now the single chain, and this was one of the systems which my colleague wanted to discuss with me. And so when we wanted to calculate electric dipole moments on the copper side, and in particular the polarization dependence, when it implies an electric field to this system, then when we were, of course, it was natural that we included these additional oxygen sites into the modeling. And I call them spectator ions because they are not directly involved in the formation of the exchange interaction. They are just dangling there. And what I have to admit, I have not realized that before writing down the formula for the Wannier states, that these spectator orbitals cause a dramatic change within for the Wannier orbitals. I mean, these are details for calculation which we needed for the electric dipole moments. So the various distances between the copper and oxides are slightly different. But what is important is these two Q parameters are just the ratios of the Hopper matrix elements, and they are very close to 1. For our purpose, we can imagine that these two Q parameters are just 1. These are ratios of the hopping within the chain and towards the spectator orbitals. And then if we write down the formula for the Wannier state, we get this normalization factor. So the spectator orbitals, they produce non-dispersive terms in normalization factor here. And so that means they remove the singularity at k equals 0. And that leads them to a wonderful exponential localization of the Wannier orbitals. And that means that one can do low power calculations, whatever one wants to calculate, in particular such properties as the electric dipole moment on the copper side. And I don't want to go into this calculation here today, but I just want to mention it was interesting to learn that the major part of this dipole moment did not arise from the ground state of these states, but it arose from an intermediate state, namely the Rice, Zinglet, and Triplet states. That produced 90% of the electric dipole moment, which implies that one would, because this is then can be considered as a correlation effect, which would not be captured by a, say, by a LDA calculation. So if one wants to calculate the electric dipole moment just using a band structure calculation, that would probably lead to very poor results. And so that was one of the results. So this dipole moment is a strong contribution, a leading contribution, major contribution from correlation effects. Okay, the Wannier state, one can look at in detail, that's not so important. And what is here? Oh, well, this is just, if anybody wants to know how one calculates these asymptotic formulas, I tried to prepare this transparency, but I probably can skip this. I mean, the next example is was a letter which my colleague also was interested in, and the same thing happens. I mean, I think I don't want to go into details here. You see that in the letter one has then lag orbitals, one has run orbitals, and then one has spectator orbitals here, down here, and of course up there also. And if one does the calculation, so the unit cell is of course now larger in this ladder, two-leg ladder system, and well, I mean, I just skip it in particular because the formulas, there is some discrepancy between my computer system and yours. Sorry about that. Run your functions. Well, let me then.
Can you show the percentage of
yes.
the spectator?
Yeah, so you see that there is, of course, already due to this geometric asymmetry, there's a difference between the occupation of these and these run oxygen states and the spectator oxygen state. Now, this is, of course, without the presence of an electric field. It's just such effects are not all easy to be calculated. Well, with the fourth example, I wanted to just briefly indicate that one is not confined to cuprates, and so this nickel system some time ago, 20 years ago, was popular because I think that if one doped it with calcium, then it did not get a metal, but there was a lot of low energy spectral weight in the infrared spectra, and so probably it was not a metal because it was too much disorder in these samples. And if one looks at the low energy sector of such a system, then the TJ model has a T-term in which not magnetic and in a singlet state exchange their side, but there are two states, and in the nickel case as a spin 1 and a spin 1/2 state which exchange side. And that is known as Zener exchange or double exchange. And so that's the reason why I wanted to. And of course, double Zener exchange is a strong mechanism for ferromagnetism. And so the idea was then that if one dopes this system, that the chains get ferromagnetic. And I don't know if that was, I've not followed up the history of the system, whether that was finally found in the system afterwards. I only remember. Yeah. Okay. Okay. So I mean, in this case, well, that's the structure of this compound. Here the nickel, the nickel 6 octahedra are attached along corners of the and so you get chains. Do I have a picture of that? Well, no, I mean you get chains which, well, yeah. So here, I mean this is the red one is a nickel orbital in which there's one hole, and the direction of the chain is now vertical, and so you see that the yellow ones are the oxygen orbitals which are involved in the superexchange along the nickel chain, and there are 4 spectator orbitals around. Yeah, and these are the 4 orbitals here around this direct. No, in here. These 4. These 3 of them are visible here. And so that is one one of the whole orbitals on the nickel side, and the other orbital on the nickel side is the central orbital in this cluster, and this this hole does not move at all. There's no mechanism for motion of this hole. So that is a spectator state as well, together with its oxygen neighbors. And so then one can do this calculation for that one, and well, it doesn't.
Nickel is 3D8.
It's 3D8, there are two holes. It's a spin one. It's a spin one.
So where are the two spins in your orbital? Which are the d orbital?
Yeah, with the two spins. I mean, so there's one hole here and one hole here, and the spins are, according to this rule, are parallel to each other, form a spin one state. Yeah, but nevertheless, I mean, of course, this orbital here is coupled to the rest of this, and only via Hund's rule. And so via Hund's rule, it influences, of course, the dynamics of this orbital. And that's so.
There is a d orbital.
In the middle there is a d orbital, right? And I only didn't color it differently because the whole is static and cannot move anywhere except to spectator ions. Yeah? And so that then would lead to a double exchange picture, and all the formulas are not visible anymore. But you get again an exponential localization. Of course, you have spectator orbitals around, but it's clear that this mechanism is very general, and so one can deal all kinds of three-dimensional system. One has a better the Wannier states are better localized than in the group rate planes. When I once told this story to Amnon Aharon, he said, well, what about the group rate planes? Can't one use the apex oxygen as spectator orbitals? But it doesn't work because they don't couple the rest. And so don't produce that. Well, that is my story, essentially. And the summary can be very short. We have seen that sufficiently realistic modeling of a low-dimensional system leads to exponentially localized Wannier functions for these hybridizing to P states, and so the Runge method works very well if only either the exchange angles are less than 180 degrees or spectator ions can be included in the modeling. Thank you very much for your attention.
We have time for short questions.
Yeah. Yes.
There is a problem in the antinodal region.
Yeah. No, I mean, I have discussed it with George and tried to convince him that that was okay. It's true that in the momentum representation, the Wannier function in the group rate planes, let me see if we can get back, diverges at k equals 0. That is true. But that is just related to the fact that in lattice space you get an algebraic decay. And that doesn't, I mean, you have wonderfully normalizable Wannier states. And he was focusing on this divergence, but it's a divergence which is physically quite normal. And if you have wave functions which are remarkably localized, their Fourier transform are always divergent at k equals 0. If the decay is weak enough. And the decay is 1 over k squared for the Wannier function in the planes. Yeah? And so, of course, if you take the norm of that, you have an integral over the square of that, it is 1 over distance to the 4th power. That works. But I mean, the Fourier transform is therefore 1 over 2nd power, and that in 2 dimensions diverges logarithmically.
So how does the energy difference between the Wannier singlet and triplet depend on the spectator oxygen atom?
you see, I mean, the sunrise ringlet and triplet are just properties of the unperturbed part of the rest of the on-site part of the Hamiltonian.
Right.
And so the spectator ions are part of the hopping Hamiltonian.
So it doesn't influence the...
Well, I mean, yes, you are right. I mean, the T0 and the T0, the little on-site term. Well, but I mean, there's, let me see. Yes, I mean, the effective hopping then gets larger because the on-site term is closer to 1. So and it gets somewhat larger, and so this splitting will then be slightly not. But these are small.
I see.
I think small effects. They are not of any major importance. I mean, small numerical effects.
Because we are thinking you have a central spin and a hole running around 4 oxygen.
Yeah.
So the singlet coupling will be weaker when you compared to when you have just 2 neighboring oxygen. So I thought the splitting will become stronger.
Yeah, sure. But well,
maybe we can discuss.
Yeah, we will discuss that.
So I'm going to close this session. I think let's thank the speaker once again. The next talk is going to be given by Dr. Kavita, and he's from Indian Institute of Technology, Karakoram, for